Hello, everyone. I appreciate giving me this opportunity to present our work on self-cleaning coating. My title is Preparation and Characterization of Superhydrophilic Self-Cleaning Coating for Solar Cell Cover Glass Applications. Firstly, please give me some time to introduce myself briefly. My name is Jian Zhou. I was born in China on August 6, 1983. Now I'm a lecturer from Shijiazhuang University, Hebei Province, China. These are some publications of mine. There are 6 teachers and dozens of students in our team, with Professor Li Jieci in charge. Here is me. The basic information of the teachers have been listed in the table. This is our lab, with about 1,000 square meters area and 3,115,000 RMB fixed assets. By the end of 2021, a new laboratory has been completed with a 300,000 RMB investment. These are some laboratory equipment, including oven, balance, and so on. Here are some communication photos with other companies and academic institutions, including China Railway Rolling Stock Corporation. This is Oriental Yuhong, a manufacturer of proof materials in Tangshan, Hebei Province. This is Jingdong Cable Limited Company, a manufacturer of cable in Xingtai, Hebei Province. This is Professor Wu from Shijiazhuang University visited to us. Now I will introduce our work. As we know, solar energy development and utilization is one of the mainstream directions of new energy development in the next few decades. There are institutional predictions photovoltaic power generation will account for 10% of the global electricity generation by 2030. However, the output performance of solar power plants can be greatly impacted by the accumulation of solid on the protective glass layer that shields the active solar cells. Solar irradiance is likely to be reflected and scattered by dust or dirt particles, inhibiting light transmissions to the solar cell, and subsequently leading to detrimental effects on the photovoltaic cell output and solar panel efficiency. Gauss described some pollution conditions, including minimal dust in the desert area, bird droppings, algae, lichen, mosses, or fungi, pollen in wet and moderate climates, engineering exhausted from an industrial area, agriculture emissions. The median degradation rate is about 0.5%, meaning that solar panels will fall by 0.5% a year. In Yusuf's paper, 13 contaminants were described in detail, including ash, bird droppings, carpet dust, cement, charcoal, clay, coal sand, laterite, loam, salt, sandy, stone dust, and wood dust. Here are the SEM images of them. Currently, people periodically clean them manually or automatically, but it is limited due to high cost. We are trying to solve the problem by using the self-cleaning method. When a liquid drop is placed on the surface of the solid, the shape of the droplet is determined by balance from the 3 forces of solid, liquid, and vapor. The line tangent drawn as a curve of the droplet to the point it intersects the solid surface forms the contact angle. A droplet with high surface tension resting on a low energy solid formed a spherical shape or high contact angle. Conversely, when the solid surface energy exceeds the liquid surface tension, the droplet forms a flatter, lower profile shape or low contact angle. The relationship between the solid gas solid liquid gas interface tension, and the contact angle could be described by Young's equation. While the contact angles predicted in Young's equation are only suitable for flat and smooth solid surfaces, the actual solid surface may be rough and uneven. It requires a correction by Wenzel or Cassio equation in actual situation. Based on the contact angle theory, there are three typical self-cleaning methods. The first one is the famous lotus effect. The surface of lotus leaf has a micro-nano structure and covered with a hydrophobic waxy matter. Water droplets on the surface do not infiltrate but remain base-shaped. As the water drops roll down, the dust will also taken away, leading to a self-cleaning effect. The second embodiment is photocatalysis, superhydrophilic self-cleaning. Since titanium dioxide has a photocatalytic effect, the photocatalysis self-cleaning has been reported in extensive literatures. The active oxygen species and hydroxy radicals are produced after light exposure. The superhydrophilic state could be formed while it returns to the original state when the light exposure stopped. The third strategy is to change the roughness of the surface according to Wenzel equation. To increase the roughness at a high-energy surface is an effective strategy to reduce the contact angle. Besides, some plants can absorb water because the leaf surface has a porous structure, leading to superhydrophilicity. This case applied to Cassio equation. In the experiments, we synthesized a silicon soot and took it as a raw material to prepare a self-cleaning coating. FTR was used to confirm the existence of silicon oxygen-silicon bonds, and TM was used to characterize the silicon soot's morphology. It showed that the silicon soot was spherical shape and showed irregular agglomeration. The superhydrophilic coating was prepared by direct mixing process. The prepared silicon soot was mixed with several solvents, surfactant, and adhesion promoters. We discussed the effect of three adhesion promoters in the formulations in detail because it played a key role of increasing the durability. Then the superhydrophilicity coating was applied on one side of the glass sheet by spin coating, wiping, or other methods. The morphology of coated surface was analyzed by SEM and AFM respectively. It could be seen that the peak-shaped structure has been formed on the surface. The static contact angles were measured using a contact angle tester. The self-cleaning property was evaluated by comparing the coated and uncoated surfaces. The determination of the water contact angle was implemented on the coated surface not only immediately after the deposition of coating, but also for a long time after that. All contact angles were measured with a 1 micrometer water droplet at ambient temperature. The changes in the contact angles with time are summarized in the figure. This trend shows that the contact angle increased over time, meaning that the superhydrophilicity gradually decreased, but the rate decreased was dependent on the formulation. It could be seen that F3 shows optimal weather resistance. In order to verify the relationship between the contact angle and the self-cleaning property and observe the self-cleaning effect, the self-cleaning coating was manually wiped from half portion of the glass sheet using a suede cloth, whereas the other half of the glass sheet was left untreated. After drying for a few minutes at room temperature, some dust was poured evenly on the glass sheet. After a slight shake, the coated and uncoated surface was observed to be quite distinct from each other. The coated half remained clean, while the uncoated half trapped dirt particles. On the other hand, to observe the anti-fog performance, the half-coated glass surface was streamed with hot water gas. It could be seen that the coated half remained clear, and while the uncoated half covered with a dense layer of water drops. The coating has a self-cleaning property because it has formed a rough inorganic coating with 20 to 100 nanometers on the surface. It prevents water to form water droplets on the surface, but rather a thin layer of water film, which separates dirt and substrate, thus resulting in self-cleaning. The optical transmission of the substrates treated with different formulations were observed by UV visible spectroscopy. The transmittance of the three samples were about 93%, showing excellent light transmittance in the wavelength range of visible light region. To sum up, we found that the coating is convenient to apply because it could be cured in a few minutes at room temperature. The formed surface exhibited self-cleaning ability despite a slight increase in the contact angle after aging. The self-cleaning ability was retained for months. Besides, the surface shows excellent transmittance and it has great potential for application in self-cleaning solar panels. Thank you for listening. This is the end of my presentation.